We're going to continue our conversation on counting principles. And in the last video, we talked about the fundamental counting principle that essentially stated that if you wanted to know the total ways that an experiment can happen, like let's say I flip a coin and then I flip a coin again and say how many ways, could this turn out? We'd say, well, how many ways exist to flip the first coin? Well, it could either land on heads or tails. How many ways exist to flip the second coin? Either heads or tails. So the fundamental counting principle essentially says that all we have to do is multiply together the number of ways that each individual event could happen, and that'll give you the total number of ways that this can happen. What I'm going to confront here in this video is essentially what we call permutations in math. And when we talk about a permutation, what we're saying here is this. It is a rearrangement, okay, rearrangement, or it is something where order matters, okay? And so the most important thing that we can kind of point out to ourselves here is this. When you talk about counting principles and permutations, we're talking about we're rearranging things. We want to find how many ways exist to do this. So notice I say here, this is one important application of the fundamental counting principles, determining the number of ways that n objects or n elements can be rearranged or ordered. So we say an ordering of n elements is called a permutation of the elements. So the definition of permutation of n different things is how many ways you could rearrange it, okay? So in terms of how does this come into like our application here, let's go and take a look at a few thought experiments, see if we can generalize this pattern here. But it says how many permutations, of course we're using this word now, instead of this, how many ways could we reorder the letters A, B, C, D, E, and F, So here's what I'd like to do. I'd actually just like to use the fundamental counting principle. It says we have a first letter, second letter, third letter, fourth, fifth, and sixth letter. So when we talk about how many total ways exist to rearrange these things, well, what we'd have to start with is this. Well, we'd say what we'd have to do is choose a first letter. And how many letters exist for us to choose from? We say 1, 2, 3, 4, 5, and 6. So there are 6 ways to choose a first letter. The important thing to recognize here is this. If I'm reordering these things, the moment I choose a letter to go up front, let's say I put A in the first spot, all of a sudden now A is not left to choose from for the next spot, and now I only have 5 choices to choose from. So we'd say 5 letters to choose from in this spot here. And then there'd only be 4 letters here, and then 3 letters here, and then 2 letters here, and then 1 letter here. As a matter of fact, we write this conveniently as 6 factorial. So the important thing to kind of point out here is this. If you wanted to rearrange 6 things, we'll always get this counting downward pattern. So we get 6 factorial. Would this apply, maybe if I said 8 kids, I want to line them all up in a row. How many ways exist to rearrange 8 kids? Well, again, 1, 2, 3, 4, 5, 6, 7, 8. Here are 8 spots where we could line kids up. And I say, well, how many kids could go on the first spot? How many ways could we pick a child to go on this first spot? Well, I say 8 ways to do it. But then there'd only be 7, and then 6, and then 5, and then 4, 3, 2, and 1, okay? So essentially, this pattern pops up so much that we say, look, this distinctive pattern with factorials would tell us that if we wanted to find the number of permutations or arrangements of n elements, n things, then really all we need to do is this. We could just take that number of elements and factorial, okay? So as far as like actually evaluating these things here goes, we could say that 6 factorial, and I should have done this here, we say that there are 720 ways with which we could rearrange the letters A through F. And then we say 8 factorial. If we do 8 factorial, is kind of a larger number here. We say 4320. So we say 40,320 ways in which we could rearrange these things. So what I want to do is I basically want to kind of generalize this. We say if you ever want to rearrange n things, it's just n factorial. So what happens here is I'm going to change the situation a little bit. And we're going to say, well, what if now I'm not rearranging all of the elements of this thing? So consider this situation. It says 8 horses are running in a race. How many different ways exist for these horses to come in first, second, and third? Now, the first thing I want everybody to notice is this. We're saying they come in first, second, and third. So here's first, here's second, here's third. So order matters here. The order in which they finish this race actually matters. So here's what I want to point out. We've got 8 total horses. So 8 of them could potentially come in first, but once a first place winner is chosen, then I only have 7 to choose from for the next spot, second place, and then only 6 people could come, or 6 horses could come in that third spot. So you'll notice that this is very much like our factorial pattern, except for what we have to do now is only do not 8 all the way through 1, 8 times 7 times 6 times 5, 4, 3, 2, 1, not 8 factorial, but only part of that factorial. So 8 times 7 times 6, we end up with 336. We're right, 336 ways. Okay. Also, this we say a coin club has 5 members, and how many ways can a president or vice president be chosen? So you notice the words president and vice president. This indicates that order actually matters here. That is, if I had 4 people running for president and vice president, it's different if I choose president, vice president, and president than if I choose, you know, like this person's the president, this person's the vice president. Even though I chose the same two people, order matters here. So again, we're going to fill this in. We say this is my pres, and this is my vice president. I say, well, how many people could come in as the president? Well, I've got 5 members, so 5 people could be the president, but once we choose a president, then we've only got 4 left over. So instead of doing the entire factorial, we just do this 5 times 4 part, and we cut everything else off. So we say 20 ways that we can do this here. So I say it is sometimes useful to rearrange only a certain number of a set of data instead of rearranging the entire set. So we say this type of reordering is referred to as a permutation of n objects. So again, down here, this was a permutation of n objects. We just said flat out n factorial, but we say take in r at a time. So essentially what we're saying is up here we had 8 horses, so we were permuting all 8 of them, except for we only needed to keep the first 3. So down here I said I've got 5 people and I want to rearrange all 5. So I'd say 5 factorial, but I don't want to keep all of the 5 factorial. I only want to keep this part of it. So what we're going to do is, in general, we're going to say this. We're going to say n is the total number of objects. Total number of objects. And we say if r is the number of objects being rearranged. Objects rearranged. Then what we could say in general is this. If I don't want to rearrange everybody, then maybe we could rewrite it elsewise. So for instance here, our formula here for permutations is n permute r. So we're saying if I had n total objects and I only wanted to rearrange r at a time, then what we'll do instead is this. Instead of just doing n factorial, we'll do n factorial over n minus r factorial. So this is our rearrangement formula. And what I want to do is I actually want to go back and use this for example 5. So for instance here we said, okay, I had 8 horses. So in the first example here we said the total objects is 8. We had 8 horses, and r is the number of these horses that we wanted to rearrange at a time. So since I have first, second, third, I've got 3 spots. And so really our calculation then becomes this. We'd say I've got 8 objects permuting 3 at a time. And so this does come out very similar to just the fact that we use 8 factorial, but it's also over n minus r factorial. And in this case, our n value is 8 and our r value is 3. So simplifying this, we end up with this. We get 8 factorial over 5 factorial, which when one writes this out, we get 8 times 7 times 6 times 5 factorial all over 5 factorial. So what happens is these 5 factorials kick out, and you can see how we get left with the same conclusion that we drew up here. Okay. So what's up with this permutation formula? Why would I rather use the permutation formula? Well, because we can do that on a calculator in general. So again, really quickly here, we had 5 members in our coin club, and we wanted to rearrange 2 at a time. So we say that 5 permute 2 in the second example would have been, well, it would have been 5 factorial over 5 minus 2 factorial, which is really 5 factorial over 3 factorial, which becomes this when written out. 5 times 4 times 3 factorial over 3 factorial. I get this here. I get 5 times 4. So I still get my 20 ways of counting this. But when you want to rearrange things, we'll use this factorial. And if we don't want to rearrange all of them, then we'll say, let's take n things and only rearrange r at a time. So that's how you calculate permutations.